First up today, we have Mr. TJ Mullen, President of Best Management Products. When it comes to BMPs, I can't think of a better name, by the way, so very good. He's been in business and president since 1999. His presentation today, Turbulence Velocity Reduction in Stormwater Quality Productions. Please put your hands together. Welcome, Mr. TJ Mullen. Thank you.
Thank you very much. How's everybody doing? We're kind of like new on the in-person conferences and shows again, so, it probably feels a little weird for all of us, but like when you're coming to these things, you never know like how many people are going to show up or what to expect, but I've been really pleased. This is a great venue, so I'm pretty happy with it. So at any rate, we're going to talk today about turbulence and velocity reduction in stormwater quality structures. And I think probably, as most of you know, both turbulence and velocity are enemies of separating out pollutants from stormwater. So hopefully we're going to talk about some simple ideas to help you make the most of your underground infrastructure. So simple goals, this isn't a long presentation, but understand how simple, you're going to hear me use that word simple a lot today. Structural methods can be used to improve stormwater quality. We're going to talk about the hydraulic impacts of water quality control devices on your overall system. We're going to discuss anti-turbulence plate product development and testing, learn how structure design affects removal efficiencies. We're going to look at how flow rate and structure dimensions affect our prediction modeling, and we're going to briefly touch on ongoing maintenance, which always is the kind of the downfall of everything with stormwater quality. We've been around for 22 years, and we got lucky. Our very first installation, like real commercial installation, not test installations, was picked up by Engineering Magazine, which is ASC East publication. So, right away we had some street cred. People were reading about a Snout at Haverford College, and back in 1999, people were still using the phone, so they weren't texting or Snapchatting or whatever. But the phone started to ring, and people wanted to know about what we were doing and how this worked out. So that was a really great break for us. In the field, it's still online. You can still look up that article. But our goal has always been to feature cost-effective stormwater devices, primarily for the ultra-urban environment. And the focus on the pollutants we're trying to get out is sediment, trash, floatables, and hydrocarbons. And at this point, we have over 100,000 installations in North America. So the question when we talk about structural methods is, well, shouldn't we just design for reducing impervious surface, and that way we don't have runoff, and then pollution reduction doesn't become as much of an issue? Absolutely, we should. But what about the part of the world that's already developed? It's always great to think about all of these great options for new construction and reducing impervious surface and controlling the environment, reducing runoff. I'm a 100% believer in all of that. But then there's the rest of the environment where we have to deal with things that are already in place. And oftentimes these ultra-urban settings just don't have the space for these land-based systems like ponds and infiltration fields. Or those ponds and infiltration fields need to be smaller, so we need to be more careful about what we put into them. The other thing about structural methods is you can tailor the tools that you throw on your specific pollutants of concern. That is, I think, helpful to both the designer and eventually the site owner, because you're targeting specific pollutants with specific designs, and that helps. Kind of going back to the first bullet point is when you're using some structural methods to serve as pre-treatment for your land-based methods, you can greatly reduce the ongoing systems maintenance, and it's really, really important to try to get as many things out of the flow of stormwater. Think of this as our treatment train effect. Get as many of the gross pollutants and solids out before you start to infiltrate and put them in your underground systems or your ponds. So structural methods are really helpful for pre-treatment. And then there's just the general concept of space flexibility. You know, you can do different things. If you have a big pond or a big underground system, that may be necessary regardless of what you're doing with pre-treatment and structural controls. But you want to make sure that you're utilizing that underground system or that pond to its maximal benefit. And by using these tools before it gets to those facilities to tailor your pollution control can save a lot of money on the ongoing service life of the facility. So the general keystone of a lot of structural stormwater quality devices is a water quality hood. And a water quality hood, our version of is something called the Snout, which you may or may not have heard of. But the general idea there is the hood covers the outlet pipe. And this is the outlet pipe right there, and this is the hood that covers it. And we have a booth down there on the floor. It's just open on the bottom. The hoods are open on the bottom. The water just flows up right underneath. But what it does is it creates a separation layer. And that separation layer is going to be wherever the static water level of the structure is. And that's going to be at the invert of the outlet pipe, okay? So your floatable oil and debris will be at the surface. Your heavier solids will sink to the bottom. And then that intermediate layer in the stormwater structure is actually where the cleanest water is. The incoming flow displaces the water that's there, it goes up and out of the snout, and it's a lot cleaner. So that's kind of the basic, that's where we start with stormwater quality in the structural system as far as our design. And these hoods can fit rectangular structures like boxes, they can fit round manholes, they come in a variety of shapes and sizes. We make them large enough to cover 72-inch pipes, and those are some pretty big parts. But there's a lot of flexibility there. So it starts there. And then we talked about hydraulic considerations, right? So now we're putting some sort of device in front of that outlet pipe, and it will have an impact on the hydraulics. Good thing is we have a model where we can input the design max flow and the design velocity. The velocity is in feet per second, and the design flow is in units of cubic feet per second. And we can get a head loss and a K factor for any pipe snout structure combination. So if you want to know what the impact is going to be, that's something that we can provide for you, which is a lot different than many other systems that are out there. You're going to slow down the water a little bit, and if you want to improve water quality, that is important, but you also don't want to flood everything upstream. So it's important that we know what the hydraulic considerations and impact on the system are. So now we're in the situation where we know we want to do water quality. We want to do water quality in a structure, and we're going to use a hood to cover the outlet pipe to get that skimming effect where we're skimming off the floatable debris, and we're letting things sink to the bottom. But we want to ramp up our sediment, our TSS removal. So then we look to increasing the surface area that the flow will see. And by increasing the surface area, we will then be able to reduce the velocity, because it's going to be the same amount of water moving through the structure. And we're going to talk about how these different components impact that particular part of the equation. So what happens is, again, the hood's a very simple concept. We wanted to come up with another simple concept that we could use to retrofit structures. So the idea to us, how many people are aware of like a sawtooth weir on top of a treatment plant intake, right? The whole goal is, it's the same amount of water flowing over it, but it's a lot more area. There's a lot more vertical space that it covers. If you stretch out that sawtooth weir, you see that the water was flowing over, 2 times the distance. So what happens, because you're flowing that water over a greater area, the velocity reduces. Well, that's what happens when you're using these baffles, right? And you're using these holes. The same amount of water is going through there, but now it's intercepting all of that surface area and all of that distance around all of those perforations. Same amount of flow, but the velocity goes down. And then when the velocity goes down, your turbulence goes down. everybody, I mean, I'm not sure, there's people who know a lot more about it than I do, but I'm a little bit of a nerd. So you look at all of these intersections with the flow and the water, and you're trying to reduce Reynolds numbers to below supercritical flow. And when you laminarize that flow, then things are going to be in nice, neat, and tidy layers, and things will then tend to separate out, rather than having basically be energetic chaos at every molecule of water, where things really doesn't know whether it's going up or down or sideways. We get things in layers, we reduce the turbulence, and we allow gravity then to impact these particles in a way that we want to control. And that's what stormwater quality is all about, right? It's controlling the environment and targeting the pollutants that we want to get rid of, and using some hydraulic tricks to put them in a place that we can deal with them and take them away later. That's it. That's all water quality is. And the amount of tools that you have to throw at it are, the more tools you have to throw at that magic trick, the better it is. And so this is just that. So we knew that the design was basically going to be these baffles. So then we started trying different combinations. We have our own hydraulics lab, and we ran different scale models, and our director of engineering, Matt White, controlled the experiments. He's down in our booth, so if you like the turbo plate, give Matt a big thumbs up. But we just ran countless number of experiments. We moved plates, we changed them, we changed the size of the perforations. The initial plate was a solid plate. We tried a perforated plate. Solid plate worked better. So we basically had a system after a number of experiments that we knew worked. The results were repeatable. If you increase the flow, the separations got a little bit less. If you decrease the flow, the separations got a little bit better. If you made the plates a little bit bigger, they got a little bit better. So we tweaked all of that and optimized the design. And then we went and brought it to a lab to do third-party testing. So now we knew how a hood and a turbo plate was going to work together. We knew that incoming plate, where you see one, that plate is going to deflect the flow incoming to the left or right. And it really doesn't matter. It's more what the configuration of each structure is, whether you deflect it left or right. And people say, oh, well, north of the equator, the Coriolis, yeah, good luck with that. It's just whatever works, where the steps are in the structure, and there's just practical considerations to whether you want to deflect it left or right. But so then it deflects it to one of the side plates. And if you look at a dye stream, you can kind of see, you think, well, what it's going to hit the snout before it hits that third plate. Some of it does, some of it doesn't. Water does really crazy things when you actually look at it in motion and time. And we tested with just one plate, we tested with two plates. We ended up getting between a 7 to 9% increase adding that third plate on the other side. So there is definitely a capacitative effect where it's still calming the water down, even though it doesn't look like it's directly in the flow path stream. So interesting stuff. But that's your basic concept with the inlet pipe, the solid plate, deflecting it to the side, and now that flow has to travel through all of that area, those open areas in the perforated plates. Same amount of flow, increased area, velocity reduces, turbulence reduces, and things start to settle out better. I know I'm going to sound like a broken record, but there's only so much you can say about a philosophy that's this simple. So, how do you design with that? So you need to think about the orientation of the inlet and outlet pipes of your structure. The most common is 180 degrees. You have an inlet pipe and an outlet pipe at 180 degrees. And that it doesn't have to be that way. It's just a pretty common, things are off axis one way or the other. And that's why I say, you don't always say you're going to have the solid plate deflect to the left or the right. It really depends on what the final orientation of the pipes in and out of the structure. And maybe things like, it could be a curb inlet, as well as an incoming pipe. Real life is a lot more complicated than a 2D CAD drawing. So we're basically going to figure out the size structure we need, the pipe size that we have, the flow that we need to accommodate. And then we're going to talk about the modeling and how we use that a little bit later. But we basically need to fit these components inside the stormwater structure with the hood always being over the outlet pipe, okay? And there's going to be a sump in the structure. And you can retrofit these parts into an existing structure if there's a deep enough sump. We recommend a minimum sump of 3 feet for pipes that are 12 inches or smaller. And then beyond pipes 12 inches and smaller, we recommend a factor of 2.5 times the outlet pipe ID. So if you have a 24-inch pipe, we'd like to see 5 feet of sump in there. And we'll talk about why that's important later. So anyway, that's your basic configuration. So you're going to design with these parts. We can accommodate up to a 36-inch ID inlet pipe and outlet pipe with the size plates that we have. It's possible. Larger pipes are coverable with custom parts, but we need to look at structures, flow, and we need to figure out how much force is going to be on those plates, because it's not an off-the-shelf sort of thing when pipes get bigger than 36 inches. So our in-house testing results were, over 50 models where we actually modeled it just with the snout, and then we started adding 1 turbo plate, 2 turbo plate, and we accumulated a lot of data. And you can see how the 2 turbo plates and 2 structures, we did 2 structures in line. You can even ramp it up even further by putting 1 structure with just the snout and then another structure with snout and turbo plates, kind of setting up your own structural treatment train. All of those options are available. But basically what happened is it allowed us to optimize our configuration. So when we went to Alden Labs, the pros, the people who really know what they're doing, we already had an optimized design that could be tested. So we weren't spending Alden Lab money trying to figure out where to put the plates and do this, that, and the other thing. We already knew the best places to do it, and we tested it. The snout alone, without the turbo plates, saw a 64% removal rate, and that's at half a CFS, 225 gallons per minute. And it was boosted to 80% with the turbo plates. And you might think, oh, 16%, that's no big deal. But what you have to consider is those are the smaller particles that are being removed. Every incremental percentage of increase means that you're removing these smaller particles that the simpler method can't remove. So every incremental step of removal is more and more difficult. So we were really thrilled that we could get there. So that's important. Basically, the particle size distribution of what we tested was from 50 to 1,000 microns, and that's what we calibrated our model with, and that's what was actually tested. And then the test flow was half a CFS in a 5-foot ID structure with a 4-foot deep sump, and that yielded 80% removals. Now, what we did is we correlated, and there were multiple tests at Alden that we did. So we dumped all of the data from Alden and our in-house testing into a gigantic spreadsheet. And we modeled, and we were able to establish a relationship using the modified overflow method for sediment reduction. And we used our hydraulic consultant is a professor at Ohio University, and we modeled and we crunched and then we validated our numbers and came up with a really good predictive software model where you input flow rate, you input structure size, you input sump depth, pipe sizes, and the BMP components. And by that I mean one size hood versus another, one certain size plates versus another. And then you put it into the model, you let it chug, and it'll come out with performance predictions. So The way it works in the real world is somebody will come up to us and say, look, this part of the treatment train needs to reduce 65% in TSS. And we're like, okay, great. So, tell us what your flow rate is. Tell us what size structure you think you'd like to use, and we always need a bigger structure once we run the models. But tell us what size structure you think you want to use. What are your pipe sizes? What are your flow rates? And what are your treatment goals? So that we'll go in and we'll just start tweaking those numbers and look at what happens when we vary the sump depth, for instance, when we vary the structure ID. And all of those different parameters are affecting the storage volume in the structure, which has a pretty, I know I'm walking away from the mic. Is everybody can hear me okay? All right. Which all of that varies the performance of the system because it all works together. In this case, we were looking for a 65% treatment goal. The flow rate was 1.05 CFS or 471.27 gallons per minute. We looked at a structure diameter of a manhole. This is a round structure, 5-foot diameter and a 5-foot sump depth. And then we ran the modified overflow rate, and we came up with a relationship that yielded a 67.87% removal rate. Don't hold me to those last two significant digits, but we felt confident that we were meeting that treatment goal at that flow rate. So how do you tweak things, and where do you get to different removal rates? Well, we had another project in Georgia where the goal was an 80% removal rate. The flow rate there was, in this case, the water quality flow rate was 0.18 CFS, and we said, look, that's a really, really low flow rate. Let's shoot for the 1 year storm, and let's look at that. And that turned out to be just shy of 1 CFS, or 0.95 CFS at 426.39. I've had the conversation about how flow rates and models are changing so dramatically with the intensity of storms increasing. And we always try to over-design when we can, just to put a little safety factor in there. But what we figured out was we needed to have a 6-foot inside diameter structure with a 7-foot deep sump for that 1 year storm to give us a removal rate of 80.33%. So what we do then is we'll say, look, that's our recommendation. If you want 80%, this is what you're going to need to do. Now, you could use a bigger structure with a shallower sump, and that we make hoods that'll fit all different size structures. So that's, those are different options. And we typically just want to have that structure have enough total volume, which is a combination of the area times the sump, that will meet the treatment requirements. And that's really up to the engineer or the end user. But there again, we tweaked it, and we were able to come up with an 80% removal rate. So these are just some examples of how, with just using 1 CFS flow, how the impact of structure depth and structure ID has an impact. So for instance, at 1 CFS, a structure that has a 6-foot ID and an 8-foot depth for 1 CFS could yield 81.64% removal rate. Now, if we reduce that structure size to a 5-foot diameter structure with a 6-foot sump depth, then that removal rate goes down to 72.89% for the given pipe size, and we're keeping all the internal components the same. 5, is that what we're saying? So at any rate, that just kind of shows you how those relationships work. Maintenance considerations, super important. When you're thinking about a structure that has that you're capturing pollution in, and let's say you have a 4-foot deep sump from the invert of the pipe down to the bottom, okay? You really have about half that structure depth as useful storage. So if you have a 4-foot deep sump, you're thinking in terms of a max of 2 feet of actually really being able to store stuff. Because at some point, you're going to hit a steady state where the stuff that comes in just kind of gets flushed right out by what's coming in. So, you have a 4-foot sump and you think, oh, I have all this storage volume. Well, you have that volume, and it has a capacitative effect to allow things to settle out. But what's going to happen is you are decreasing your efficiency because at some point you're going to hit a steady state. So it's important. That's why I put the clean it out when there's 2 feet of material or 4 foot deep stuff. You're going to find that structures with turbo plates are going to obviously collect a lot more sediment faster. We are on social media. My social media guru Ty is back there. So check out our LinkedIn page and please like us on Facebook. And that's pretty much what I have for you today. So I hope that was helpful. And if anybody has some quick questions, I'd be happy to address them with you. Well, thank you. You've been a great